Hello and welcome to our next session. This one is going to be on tessellations. Let me just position my GIF here in the best possible way. Maximize our screen space. That should be okay. Check the sound here. Okay, sounds good. So this format will be maybe a little different than the previous ones, where I mainly have a slideshow that I talk over. Like I said in this topic, the presentation side of things are a little more mixed, but it depends on the topic. This topic certainly is something that is very nice to have that knowledge for elementary school, since I can make little craft projects and things that engage students much more, but it's not a calculation heavy topic. So pros and cons, right? All right, so let's go. So when you look around in the world, in like floor tiles of um, older or more famous buildings and areas, you see basic geometric shapes being repeated in interesting ways to fill the floor space. Here you can see some squares and triangles. Uh, and what is this guy? One, two, three, four, five, six. A hexagon laid out. Here you see some other shapes. This is a triangle and hexagons again. So different shapes can, copies of the shape can be laid out in a tiling to fill the floor. There's no gaps between these tiles. And of course, you can get more creative in terms of the shapes and step a little bit away from polygons. The sky's the limit, really. But we, for this first introduction to the concept, want to keep things fairly contained and simple by just focusing on polygons. In nature, if you look at a beehive, nature has naturally gravitated, in the bee case, to hexagon, optimizing the balance between space and resources used, and disregarding the little gaps in between, of course. To construct this beehive, the hexagons fill the, the space that the bees work in. On this tortoise shell, you also see similar shapes being repeated to fill the shell. Of course, a little more 3D, not perfectly the same copy every time, but that idea of a geometric shape filling a surface is sort of the underlying theme here. So, what we often do, we observe these things and we say, let's simplify it and give it a name, try and quantify this and see, excuse me, and see what basic conclusions we can make. So we're going to call this a plane tessellation. Plane, because I'm working on filling a flat two-dimensional surface called the plane. A tessellation is a perfect covering of this flat two-dimensional plane made up of repetitions of regions or figures in general. That's what we'll call a tessellation. Now we're only going to work with a plane tessellation, so I'm not going to say that word every time. We'll just talk about it as a tessellation. It has to be a perfect covering, meaning there's no overlapping of the shapes that I use, and there are no gaps left. It fills it perfectly, covers it perfectly. Now, in some cases, I can use multiple shapes, copies of just one shape. If I make a tessellation, this perfect covering, and it consists of the repetition of only a single shape, region, figure, then we say, like a square, for example, then we say that shape tessellates the plane. And we call the covering that we get, the design, we call that a tessellation. Right. So that's going to be the wording for this topic, this concept. Let's look at some interesting examples and ask a couple of initial questions. If I look at this image, which shapes are being used to fill that image? It has a three-dimensional look to it, but it's just an illusion. By coloring these parallelograms a certain way, arranging them, I create the illusion of three dimensions, that these are actually cubes, but they're not. They're just an arrangement of parallelograms in a tessellation. So on top of the basic shape being used to fill the plane, to make a tessellation, I can color it and shade it in creative ways to create more interesting visual appeal. So the follow-up question then is, okay, the parallelogram is certainly used here. These shapes, I can visually just verify that they're parallelograms. They certainly look like it. Can any parallelogram tessellate the plane? Now I have to understand that sentence. I have to understand that question first. I have a shape. I'm asking if it tessellates the plane, meaning can copies of the same parallelogram, regardless of what that parallelogram is, can copies be used to fill a flat surface indefinitely? So I have to get the wording right first. Well, let's just go all the way ahead to my page, which is not the next page, on parallelograms. And yes, I can get a little creative and it'll look and can make a very nice look to the tessellation. But if I just look at the left one, I can see that I can make columns in this case of the same parallelogram, just alternating colors for my convenience. It's the same parallelogram being copied, row, rows or vertical rows, I guess columns, and then just line up the columns next to each other. And I can keep doing that in either direction forever. So I therefore conclude this was not depending on the specific parallelogram. I can do that for any parallelogram. So any parallelogram tessellates the plane. Regardless of how I color it, it is copies of the same shape. I can orient them in different ways and still tessellate the plane. I'm not saying this is the only one, but any basic strategy I can come up with that works, and I can conclude that any copy of that shape would work. It's not necessarily the only way that it could work. All right, so our main objectives are to explore symmetry and properties of shapes, basic polygons, this topic of plane tessellations. Sorry, I should just say tessellations. It's always going to be plane. And then ask the next question could be, well, I know my basic polygons. I hope I know my basic. Which one of them or which ones can be used to tessellate the plane? Or do I have to use combinations? But let's stick to the basic ones so that we can answer that question more easily. And we can also ask sort of an afterthought question leading to maybe something you want to keep in the back of your mind for future elementary school projects. How do I make one myself without just sticking to specific basic polygons? There's a little example here just to get those creative juices flowing in your head. But that's not what we're going to look at initially, right? We want to start things very simple to get a handle on this and then build from that. Understand this, for example. So, what is the most basic shape for the tessellation question? Probably the square, because I've seen it before. I see it in actual bathroom tiles, for example, that there is no doubt that the square tessellates the plane. I have physically seen it out in the world. It works. I just stack them and I can fill any flat surface. Of course, in an actual tiling, there's some gaps, but that's just for practical reasons to actually stick the tile to the wall or the floor, right? Theoretically, it's not needed. Copies of the same square can be used indefinitely to fill the plane. Well, then the next step from a square, a little more general square, rectangle. Yes, of course, I've seen those before as well. Bricks, making a wall. I can arrange them in more interesting ways, but as long as I find an arrangement that can fill the plane, then the rectangle tessellates the plane. Okay, so basic shapes. The news is pretty good. News is pretty good. Far, so good. We have covered then a direction to make the rectangle more general, thinking of our hierarchy of shapes. The parallelogram, which we have already discussed. Okay, good, good. There. So we have some familiar polygons that certainly make solid tessellations. And I have something. It's not that hard to come up with a tessellation. Let's go maybe down a step to a triangle, which is kind of the first polygon. Before we make it bigger and bigger, let's just cover the one we missed, the triangle. Now, I encourage you to, especially because we're thinking of elementary school, we're thinking of being a teacher in a classroom, and arts and crafts and learning through discovery is a very important aspect to our teaching. And geometry really gives an opportunity uh, for that kind of learning. So I don't want to miss an opportunity. Feel free to get in touch with your arts and crafts side and pause and go and take a piece of paper, make copies of your favorite triangle. It can be an obtuse scalene triangle, it could be a nice equilateral triangle, right angle triangle, isosceles triangle, a cute triangle. See, you can choose whichever one you want because I don't want only the tessellation to work for a specific kind of triangle. I want to make at least a statement general enough to cover all triangles. So feel free to make any copy, but make sure it is the same copy, right? So if you want to play along, take a piece of paper, make copies of the same triangle, cut them out, make it interesting, and maybe you're back having paused and done that. Now play around with them on the table. The downside of this online session is we can't really get hands-on with paper and arts and crafts, right? But we can imagine it. Now, if you have your triangle, one copy, not all of these, you pick one. Let's suppose I picked that one. Copies of that triangle. How can I arrange and stack them to fill the table in front of me? Actually, pretty simple. Because we have seen before when we talked about our basic area formulas, we've mentioned that a triangle and its flipped version will always make a parallelogram. And we know parallelograms tessellate the plane. If I can make parallelograms and stack them, I have indirectly stacked my, or let's say tiled, not stacked, tiled my triangles as well. So any triangle will create a parallelogram when I double it up. Parallelograms always tessellate the plane, so therefore any triangle will tessellate the plane. But keep this, make a mental note that this is a very good experiment to do with your elementary school class. Keep them busy for hours. Cut out the triangles. Once they have that, then lay them out. Can I arrange them so there are no gaps? Can I find the link between triangles and parallelograms? Discovery. Discovery. We might not uh, do all of those things because you're not an elementary school student, but make mental notes of the opportunities that geometry gives me to have that discovery learning, more so than other topics within mathematics. So let's open it up. Let's make it general. Any quadrilateral. Give me any random quadrilateral. This black one over here is not that big, but hopefully you can see it. There's a little link here. I don't know if this link works anymore, but I have a picture as well. That just by arranging 4 copies, well, the quadrilateral and 3 more copies, so 4, arranging them, attaching them at this vertex, I have a bigger shape. And if you see this bigger shape as a puzzle piece, you'll see the indentation at the top exactly matches the bottom. The indentation on the left exactly matches the right. And I'll be able to puzzle piece them together, filling the surface. So actually, literally any quadrilateral will tessellate the plane. That's pretty good news. Now, we don't necessarily want to play with any quadrilateral. That's a little too general, but it's good to know that I started small and very structured, slowly stepping it up, and actually there's no end. There's no restriction in the quadrilateral case or in the triangle case. So all 3-sided polygons can tessellate the plane. Great. All 4-sided polygons. Well, at least ones I can visually confirm that have a nice roundish shape. When it gets bigger, the question becomes less obvious, or the answer becomes less obvious. So what do we then do? If I look at pentagons, now I know I can get stars and all kinds of indented polygons, right? It's a little too big a question for me. How do we give it a lot of structure? By looking at regular polygons. Now I have to remember, of course, right? Chapter on that. That was my introduction. What is regular? Regular is all side lengths are the same, all angles are the same. It is as balanced and simple as I can get. And then I just change the size. So my equilateral triangles are done. My square tessellates as well. So that one is considered as well. And then we can slowly step this up. A regular pentagon, regular hexagon, bigger and bigger and bigger, and explore that, but just with a lot of structure. Otherwise, the question's too big. So if I open up the floor to any regular polygon, we already have 2 of them. We have the equilateral triangle, tessellates, yes. We have the square, tessellates, yes. How many more can there be? Because there are infinitely many regular polygons. Are there infinitely many of them that can tessellate the plane? Well, We have to explore that, but at least it's a question that I can manage now. It's a manageable question to understand and explore. Now, how do we answer that question and explore that further? To make it simpler, we have to make an observation. Now, a lot of things are happening on the slide. Don't read everything. Listen to me. Just look at the pictures. Any regular polygon, I can connect opposing vertices and split the inside of the polygon up into a number of triangles. For the square, I make this diagonal. I've split it up into two triangles. I don't care if those triangles are similar or not. In the square case, yes, they're the same triangle. In this pentagon case, no, maybe it's not the same triangle. It doesn't matter. I split up the pentagon's interior into three triangles. I can use the same vertex, doesn't matter. This isn't the only way, but I can do it. Hexagon, maybe use the same one. Maybe you use, I'm going to have to use, I could use a different one. I could make it look like this. Actually, can I draw a regular hexagon that quickly? Sure if I can. I'm going to have to budget a little bit. This might not be regular. I'm going to eyeball it. My flat sides are too big. But it's okay, you get the idea. Lines here. I can maybe do, oopsie, separate like that. I know it's not perfectly regular. Maybe like that and that. Doesn't have to look exactly like this picture. I have some options, and the bigger the polygon, the more options I have. But regardless, I can ask the question, what is the minimum number of triangles that I can see inside this hexagon? Whether I do it like this blue one, 1, 2, 3, 4 triangles. Whether I do it like this, 1, 2, 3, 4 triangles. I can't do any better. I cannot get just 3 triangles going to be split up into 4 triangles, but that can be done in different ways. And I have more options the bigger the polygon gets. So that's not the issue. The issue is the number of triangles. The number of triangles. So now notice that let's make a little table here instead of looking at the formula. Now a lot of things are happening on this table. I know. We're doing it one step at a time. Perhaps. So I have some polygons. They're going to be regular. Regular. I apologize in advance. The writing is not going to look very good. Whenever I drag in a PDF, the pen has to be really thin, and then it gets a little wobbly. Triangle, number of sides, obviously 3, right? Square, 4 sides. A pentagon has 5. Hexagon has 6. Heptagon has 7. Octagon has 8. Nonagon has 9. Decagon has 10. Hendecagon 11. Dodecagon 12. And in the process, you've learned some new words as well. Win-win. Now for the triangle, how many triangles make up its interior? Well, 1. It's a triangle already. It's nothing to do. But for the square, refer to this. I can make 2 triangles, right? The interior. For the pentagon, refer to this. 3 triangles. For the hexagon, refer to this. 1, 2, 3, 4 triangles, we said. And now you hopefully see a pattern that the number of interior triangles is 2 less than the number of sides. So a hectagon has 5, octagon is 6, 7, 8, 9, and 10. I don't want to draw all of these. I do enough to see a pattern, and then I just extend the pattern. Right? So this slide is just trying to say that if I have n sides of my polygon, called an n-gon in general, I can split it up the interior into 2 fewer than n minus 2 triangles. Now, among the many things that Euclid proved when he did the Euclidean constructions and all kinds of properties, uh, Pythagoras, everything, pretty much everything, when it comes to geometry at that level, is looking at the sum of all the interior angles of a triangle. It doesn't actually have to be an equilateral triangle. It could be any triangle. Let me just make this bigger while I write here. For, that's still not very big, is it? Let's go any, that's too big. Let's go 8. For any triangle, the sum of the interior angles, sum is 180 degrees. Now we're not going to prove it here. Uh, it's actually very interesting to see how he builds up to this from 5 basic assumptions, and everything is built on those 5 basic assumptions. One of them is if you have 2 points, you can draw a straight line. If you have a point and length, you can make a circle. Those basic assumptions that no one questions, that's what he builds up to get to more interesting properties like this. But that's a topic for another day. And unfortunately, the course is not big enough, long enough to really delve into that. So we're just going to take this as fact, which it is. Any triangle, the sum of all these interior angles, they're going to be different, potentially. It's not an equilateral triangle necessarily. If I add them up, I get 180 degrees. So now if I go back to my small pen size here. For a triangle, the sum of the interior angles is 180 degrees. It's the triangle. For the square, square-like. Now, I'm not going to cheat and say, well, I know the interior angles are all 90 degrees. 90 times 4 is 360 degrees. Well, yes, but later on I won't know the interior angles. So I can't really cheat that way. Not going to work for the pentagon, hexagon, and so on. I don't know those angles. But what I do know is that I can split up the interior into 2 triangles. Triangle 1, triangle 2. So let's say here triangle 1 will give me 180 degrees. Those guys. Triangle, that does not look like a triangle. 2, its interior angles will give me 180 degrees. So together, I have this one plus this one. So 360 degrees, which in the case of the square, yes, I knew it should be, but soon I might not. So degrees there, 360 degrees. I'll write over here that this was 2 times 180 degrees. I need this space maybe, so I don't want to go into this column. If I have the pentagon, we can see, well, there I'm just going to do the same thing, but then I have 3 triangles. So it's going to be 180, 180, 180. So 3 times 180 degrees. So it's really this number times 180 degrees is going to give me this answer. Now I don't necessarily know what that is, so let's go and have a look. 3 times 180. I apparently can't type. Wow, I'm on fire today. Just press random buttons until it decides to press what I want it to press. 3 times 180. And we get 540. Now, this isn't very important. What's important is how we get it. The hexagon, same thing, but I have 1, 2, 3, 4 different triangles. So 4 times 180. Because 180 is for each triangle. If I add that up, I get 720. And then you can keep doing that. It's however many triangles I get times 180. I don't actually, to be perfectly honest, I don't care what that answer is. Whatever this is, could not really care less. It's a stepping stone to this column. I want to know how big is a single angle in my square, in my pentagon, in my hexagon. I use the triangles to find a path to answer that, but that's ultimately my question. So a single interior angle of the triangle, well, a triangle has 3 sides and 3 angles, right? Number of sides, number of angles are always going to be the same. Because it's regular, they're all going to be the same. So if I have a triangle, where's my triangle? I have a triangle here. If it's regular, then all these angles are the same. 1, 2, 3 of them, adding up to 180. How much is a single one? I just divide by how many there are. So 180 divided by 3. Page. Here, 180 divided by 3, and I get 60 degrees. Which we kind of already knew, right? Square, we know it's 90 degrees. How do we get to 90? Well, it's adding up all the angles of the square. And we did that by way of a triangle because we didn't perhaps know the answer. Adding up them all. And now there are 4 of them. So to find a single one, I divide by 4, and that's of course going to give me the 90 that I need, that I know is right. But later on, I don't know the answer. For the pentagon, adding up all of the angles gives me 540. Now for the pentagon, there are 5 of them. And in regular case, they're all the same. So I divide by 5 to get 108. So it's the sum of the interior angles divided by how many there are that gives me a single interior angle. And in the hexagon case, I get 120. But I don't have to find this answer to divide, right? I could just take this, in the heptagon case, 5 times 180 degrees, divided by 7, and I'll get my answer. Let's do this one in calculator. 5 times 180 divided by 7. Yeah, I divide by 7. It's not going to be pretty. Let's round it to a couple of decimals. I get 128.57. Let's do maybe the octagon. The sum of the interior angles. Its calculation was 6 times 180. I take that and split it up across the 8 interior angles to find the size of 1. I get 6 times 180 divided by 8, 135. Whoopsie. 135. Okay, so it's important to know how we did this so that I can duplicate it, so that I can calculate this last column and understand how I got there. Now, I'm not going to calculate them all. I'll just show them to you. Let's drag it over here. Sure, it looks good on the screen. You can see it, but I encourage you to, of course, calculate them yourself. Make sure that you can do it. So you see the ones we got here, and then there are a few more. Make sure you can calculate this last column just for these polygons, regular, and understand how we get to this number. Right? So now that we have the ability to calculate the interior angle of a regular polygon, up to 12 at least, which is totally fine, how does that actually help us? Well, keep in mind what our question is. Our question is, and we got a little sidetracked perhaps in order to answer this question, so now we're coming back to it. Our question is to figure out which other regular polygons can tessellate the plane. We know a square, we know a triangle, but there are many others. Now, knowing their interior angles by way of this triangle argument can help us. So the next one on the in line is the pentagon, right? So now you can make this an experiment, make this a little bit more interactive, just like we did for the triangles, and cut out some copies of a pentagon on a piece of paper. We have to make sure it's regular now, right? In the case of the triangle, it could have been any triangle. Now we have to be regular. So it has to be perfectly balanced and symmetrical and so on. Am I able to make a pentagon? And why not? Or why can't I? The problem is that if I want to tile this shape on the screen, on the table, they're going to have to come together at a point. And if I try, because of what the angle, let's look at this diagram first before reading, because the interior angle of a pentagon is 108 degrees, if I start attaching them, I can do 3 of them, but 108 times 3 does not give me a full rotation, a full, uh, well, should I say, revolution all around the point where they're attached. It doesn't get me to 360 degrees, which is all the way around. It leaves a little gap of 36 degrees. And I can't use another pentagon to squeeze it into that gap because I would need 108 degrees and I only have a gap of 36 degrees. So I'm left with a gap, and therefore the pentagon can't be used on its own to tessellate because I have this gap. So that concludes, okay, the pentagon can't be used on its own, fine. But it also leads me to the requirement for a regular polygon to work in this manner. That when I attach them, I have to have no gap. So the interior angles have to add up to 360 degrees. And because I know the interior angles, I can figure out which ones would work. So here's just some of them as a reminder in a different kind of table. I have my equilateral triangle, interior angle 60, remember, and I could tessellate them because if I add up enough 60s, I'll get to perfectly 360 degrees. The square works because if I add up 4 of them, I get to 360 degrees. Pentagon doesn't work because it doesn't add up to 360 degrees. The hexagon is going to work again because its interior angle is 120 degrees. Three of them stacked together, attached in this way, will bring me all the way around with no gap to 360 degrees. Pentagon falls a little short, regardless of how many I do. I could overshoot it or I could fall short. I can't get to 360, but the hexagon does. We're using 3. Octagon, you see the picture here. Now, if I attach 2 of them, I have a gap, and that gap is too small for another octagon. Regular tessellation can only use the single shape, copies of that shape. And if I go bigger, the problem just gets worse. And I can never fill the page, fill the screen perfectly again. So the only regular tessellations that are possible is that of the triangle, the square, and the hexagon. Because of what the interior angles are and my requirement to use one shape only over and over, I cannot use any other regular polygon. There are only 3 regular tessellations. So, what do I have to know? I have to know what a regular tessellation is. I have to be able to draw these pictures in terms of how they stack around each other or tile around each other to show how the tessellation would look if I keep extending it. So I only need to worry about a single point where they're attached, because that is going to be the same for any other point over and over and over and over. So these 3 figures to represent graphically the regular tessellation. And I also have to know, of course, the interior angles of all polygons to be able to argue why the others don't work, this 360-degree requirement. So now you might say, okay, that's fine, nice, only 3 of them, that's good. I understand the argument. However, if I look at this octagon and the gap that it has, well, that gap will fit a square perfectly in there. So I could say, okay, let's relax the strict requirement of a regular tessellation, requiring that I can have copies of one single regular polygon. Let's relax it to more polygons. What can we do then? Well, then our options open up. And we're going to call it a semi-regular tessellation. It's regular in the sense that the polygons that I'm allowed to use are all regular polygons. However, I'm not restricting myself to just one type. So if I look at this blue one, I'm creating a tessellation using squares and triangles. And this is more than I need to show, but it clearly shows enough that it can be extended in either direction, filling the plane perfectly. And if I look at this red one, I'm using hexagons and triangles, and that can be continued forever. So by allowing more than one shape, I'm able to have more variety and more possibilities. So the requirement is that I have to use multiple regular polygons, but also that the tiling has some consistency, that at any vertex where the vertices of the shapes are connected, it looks exactly the same. So if I zoom in a little bit, in this blue one, if I look at where my hand is, that vertex has 3 triangles and 2 squares attached. This vertex has 3 triangles and 2 squares attached. This vertex, 3 triangles and 2 squares. Every vertex where they are meeting have the same property. 3 triangles and 2 squares. They're all the same. If I look at this vertex, for example, in the red, I have a hexagon, a triangle, hexagon, and a triangle. Over here, Hexagon, triangle, hexagon, triangle. They're all exactly the same where the vertices meet. So I have a couple of options. Let's see if I have space here. I do. I have a couple of options in terms of how to name or represent these tessellations. I had my, let's say the blue one. Let's see how perfect. It's a freehand drawing here. I have my triangle. If you look at what it looked like, let's go and just see it again. Trying to look at that vertex. What's happening around that vertex? So I have something like this, like that. And there are my three triangles. Again, it doesn't have to be perfect, right? That's what it looks like around this vertex. So first of all, I have to be able to copy this and draw this for what happens around a single vertex for that semi-regular tessellation. And I can also give it a more symbolic name. We're going to call it the vertex figure name. All I'm going to do is the same thing, but symbolically. For a triangle, I'm going to use the symbol 3 for obvious reasons, because a triangle is a three-sided polygon. I'm going to use symbol 3. It's more a symbol than a number. And for a square, I'll use the appropriate symbol 4. I'm not making new symbols, I'm just recycling digits and pretend they're the names of these shapes. Then I'm going to make a start. I'm going to pick this one. It doesn't matter where I start as long as I go all the way around. Start there, there is all the same. And then I'm going to just list the names of the appropriate shape in the sequence that they go around, that they attach around this point. So 3, then I'll put a little dot there. 3 dot 3, because triangle, triangle, triangle. Then a square, then a square. That's going to be a symbolic name for the exact same thing. Because I don't always want to draw pictures, I don't always have the skill to draw pictures or the space or anything, right? If it's in a sentence, a symbolic name like this fits nicer in a sentence than just inserting a sizable figure mid-sentence. It looks a little weird sometimes, so it's nice to have the option. I could also, of course, start at a different spot. I could start at the square here, for example. 4, 4, 3, 3, 3. Right? So there's a lot of variations, but essentially it's the same. The order matters. How do I attach them? How do I attach them? Now, just be careful how you read this. This is not actually a number. I'm not actually multiplying, or this isn't actually a decimal point. It's just a separator. It's just a name. But to make it even more confusing, because why not? They thought, well, this is a little long. I don't want to write 5 things. If I exploit the exponential notation as if this is multiplication, which I know it's not, I could say, well, there are 3 3s and then followed by 2 4s. But this is still just a symbolic name. This is not a calculation. Not a calculation. This is not 3 to the power of 3 times 4 to the power of 2. No. People are just so lazy, they want to condense it as much as possible. You can completely ignore that, or you can use it if you understand that this is not a calculation, it's just a condensed name of this more stretched out detailed one. I don't even actually know how you say it, where this you could say 4 4 3 3 3. This one, don't say 4 squared, because it's not. I don't really know. It's just for looks. I would say it like this. Vertex figure name. Vertex. And then, of course, I can go back and say, well, okay, what is the, where am I now? Let's zoom out a touch. What is the vertex figure name of these regular tessellations? Well, it's the same shape every time, right? Go around as long as you list the correct number of them. 3, 3, 3, 3, 3, 3. 4, 4, 4, 4. 6, 6, 6. Because there's only one shape. Repeat it. But it turns out that if I have semi-regular tessellations, my options open up more than just these two examples. And you can see some examples actually used. And it turns out that there are 8 different semi-regular tessellations. You can go and explore and see if you can find some and take a picture and share it with us on Discord in the chat channel. But here are all 4 and another 4. So I've seen this one before. Can use some octagons, and then I have a gap perfectly of a square. Yeah. Don't worry about the things in the brackets. I should remove that. That's something completely different. There's my vertex figure name in condensed form. 4, 8, 8. This third one I've seen, it was the blue one. I can use a square and 3 triangles in a slightly different way. Squeeze in a triangle in between the 2 squares. The vertex figure name changes. Even though I'm using 2 squares and 3 triangles in both of these, the vertex figure name and the figure itself is not the same. Different tessellation. I can use a hexagon and 4 triangles. And then let me just finish. Let's not look at the blue ones yet. I can use a hexagon, 2 squares, and a triangle in this way. Now, proving that these are the only 8, that's not an easy question, right? This one we've seen. This one we've seen. That was the red one in our first example. And then there are 2 semi-regular tessellations which uses a 12-sided polygon as well. A little bit more difficult to draw because it starts getting a little circular when I have that many sides, but they do exist. They do exist. So I have to know that there are 8 of these semi-regular tessellations. I have to know what semi-regular even means. I have to be able to draw these little figures and state their vertex figure name in whatever form. Understand what they consist of. I'm not going to ask you to draw the 12 one because that's hard. That's hard to do. But there are many others to choose from. So make sure you understand what the difference is, what I'm allowed to do, why some of them work regular tessellations, why some cannot be a regular tessellation. Uh, and it's more of a knowledge topic than a calculation topic.